The broadcast is now starting. All attendees are in listen-only mode.
All right, Paul, you can jump right in.
Good afternoon, everybody, and welcome to the next edition of Just Ask Paul. My name is Paul Branteon. I'm the Director of Research, Education, Technology here at the North American Die Casting Association. And we're going to be going through a handful of questions today and then detail answers on those questions. So to start right out, we're going to go to the first question. And the first question says, we have experienced sludge buildup in our launders during the extended shutdown. Some plants experienced it earlier. We have cleaned the launders 1 to 2 times per week and have maintained the temperature. How does time affect the precipitation of sludge? So instead of just jumping into the answer, I'm gonna go through sludge formation, and then we're going to talk about the answer to this. So the first thing is, we see sludge buildup in our furnaces, and that sludge buildup can be on the bottom, along the melt line, and anytime we get any of this buildup in there, it's going to reduce the effectiveness of our furnaces. So maintaining cleanliness, keeping the furnaces clean, keeping temperature, that's going to be very important in maintaining a low sludge buildup. So what is sludge? Sludge is the primary crystals that are our primary crystals that contain aluminum and silicon, and they're rich in iron, manganese, and chromium. These crystals have very high melting points and very high specific gravities. So with those characteristics, anything that is formed, these intermetallics that form, are going to drop and settle to the bottom of our furnaces. So the sludge buildup can occur in any point of the process as long as there's molten metal. So it can occur in the main furnace, in your reverbs, your breakdowns. It can occur in your holding furnaces. It can occur in the launder systems. So here we've got a picture of a launder, and it can occur in these launder sections. It can occur from the point the metal is being ladled. So in the ladle cup, in the cold chamber, and even as much as into the injection in the die cast dies. The biggest difference is going to be the crystal size. So when sludge starts to form, if it's not agitated, if it is not solidifying rapidly, like in the die casting, then the crystals are going to grow large. So we're going to have large crystals in our holding pots, in our launder furnaces, in our launder sections, in our breakdown furnaces. And those large crystals are forming because it has plenty of time to grow. So as we look at what sludge is, this is work that was done by John Jorstad. And John came up with this equation. And this equation basically tells us when sludge is going to form. So sludge formation takes place when the iron content, the manganese content, and the chromium content. So 1 times iron, 2 times manganese, 3 times chromium. We're taking a spectrographic reading of our alloy, getting the chemistry. We can then calculate a sludge factor. Anytime that sludge factor is above 1.8, that's when we start to see higher than normal sludge formation. So we can see a graph like this, and this graph represents a holding furnace, and that holding furnace is operating between 1220 and 1250 is our set point. So we have a total of a 30-degree range. So plus or minus 15 degrees. So 1235 to 1250 down to 1220. And sludging is going to occur anytime the metal temperature drops below this line based on the sludge factor. So on the bottom of the graph, we have our sludge factors, 1, 1, 2, 1, 4, 1, 6. Here's that 1, 8 region. And as we look at that 1, 8 region, so at 1.8 sludge factor, if our holding furnace is right around that 1235, as long as we maintain 1.8, then we're not going to see sludging, or sludging is going to be at a tolerable level. And we're not going to have excessive sludging. Excessive sludging is going to occur when that sludge factor increases. So we've still got the same holding temperature, and now all that we've done is we've moved our sludge factor from this 1.8 region all the way up to this 2.2 region. And when we move the sludge factor, maintaining temperature, we're now have a very high sludge factor, and sludging is going to occur in our furnaces or at any point in our process. Okay. Sludging also occurs when that metal temperature drops. So if we're holding our holding furnace at 1235, then we ladle, we hold it in our ladle cup, we have a pour delay, and then we finally pour it into our cold chamber, and then we have a shot delay, and it's sitting in the cold chamber, the sludging is going to start. So this is now our injection temperature. So up here was our holding temperature, and down here is the temperature of the metal as it's going to enter the tool. So as the metal enters the tool, and we have, depending on what the sludge factor is, you know, whether it's 1.4, 1.6, or 1.8, we're going to see sludging occur. So if we're holding a 1.8, then we're right about here, right about here on our graph. We're going to have a tremendous amount of sludge formation. So that sludge is now going to be small crystals. They didn't have time to sit there and grow, but they're going to be small crystals that are going to be injected into our die castings. And so any point the metal's liquid, sludge formation can take place. So we can see whether we've got our holding furnace temperature at 1.8 or our metal injection temperature, still maintaining that sludge factor at 1.8, we're going to get higher sludging here than here. So knowing what our sludge factor is, it's all going to be based on the iron, the manganese, and the chromium content. So we can see that metal temperature drop is going to increase sludging. These are sludge crystals. So these are aluminum silicon, iron manganese, chromium crystals. And then these crystals form and they get injected into our die castings. If we were to look at photomicrographs of our castings, we can see those sludge points, sludge items in our material. If we're machining these castings, we hit any of these are going to be more dense. Now, this isn't necessarily corundum level of density, but the increased specific gravity, the increased density could chip tools, can break tools, can smear the casting. So if you're machining across these crystals, just like any other imperfections in our metal, we could then affect the machining operations. So just to recap, sludging occurs when the iron, chromium, and manganese form together with aluminum silicon. These then precipitate out and they form new compounds, intermetallics. These intermetallics will not melt back into our material. Okay? And so even if we have a furnace temperature drop and we were holding at 1210 and we drop down to 1180, sludging is going to occur. We bring the furnace back to 1210. We're not going to remelt these sludge material back into solution. Okay, so they then get in our castings are going to form hard spots. Other thing that sludge does, it's going to create lower fluidity, so it's going to reduce some castability. It's going to increase soldering, and that increased soldering comes from the fact that when the iron actually combines in these crystals, the iron levels vary, and they can vary from 4% all the way up to 20%. So when you now have these sludge crystals forming, they're actually pulling iron out of the aluminum. So if you're running your iron level and you start seeing soldering, it could be as a result of sludging or sludge formation in our holding pots. Okay, it can also reduce tool life and tool life for those secondary operations. So to answer the question, how can we practically deal with this? Well, we can remove sludge from our furnaces, and that's basically just dragging, and raking the material out and getting it off the furnace floors. Remember, this material is going to sink. We want to maintain temperature control. So based on our sludge factor, so when we check our metal on our spectrometers, most spectrometers are giving us a sludge factor. Based on our sludge factor, and that Jorstad graph is going to tell us what temperatures we need to maintain at a minimum. We drop below those temperatures, we're going to start to see sludge formation. And then the other thing that we can do is we can actually correct that imbalance by adding a high purity alloy, a higher aluminum content or a pure aluminum back into our furnace. So by doing that, we actually offset the iron, manganese, and chromium percentages in the chemistry by changing those percentages, effectively lowering them. We change the sludge factor, and then our furnace is more tolerable of lower temperatures. So the question was, how does time affect the precipitation of sludge? Well, that crystal formation is going to grow, and given in launder systems or holding pots, we can get that larger grain growth in alloys like A380 and 360. The other thing that can take place is if a furnace is just sitting, if you've got like a 360 alloy or even a 380, but with a 360 type alloy, is you can burn the magnesium off. And then just by the metal sitting, you can lose magnesium content. If you lose magnesium content, then it's going to raise the percentages of the other elements. So the iron, manganese, and chrome are going to increase in percentage, and as they increase, so does the potential of sludge and sludge formation. So then once you get higher sludge factors, those can then increase additional sludging. So you can get sludge formation at the same temperature or even at higher temperatures if those percentages are increasing. So moving on to the next question, we've kind of talked a lot about sludge and sludge formation. Moving on to the next question. This is from a die caster that was having some problems, and they sent this question in. I contacted them, and then we worked through this for a several-day period to understand it so that they could understand it, and then they could start to go to work on it. So the question is, we have a product that we are having die cast, so they're an OEM, and then they take and they chrome plate the parts. So they have had 4 different platers try with very bad to somewhat acceptable results. Can you tell us if a special alloy needs to be used or if something else is required? Basically, the chrome keeps having bubbles develop underneath the copper layer. So I contacted this company, started to work through this. The easy answer would be, hey guys, just reduce the porosity in your casting, and that's going to eliminate the bubbles and not affect the coating. So instead of just throwing that at an OEM, I started to discuss the problem with them, and then we involved the OEM, the plater, and the die caster in looking for a solution and then working towards that solution. So in doing that, I found out some things I didn't expect. And the first is, the part is Zamac 5. That's understandable. A lot of chrome plated parts are made of zinc. So that wasn't a surprise. But they have this problem in Zamac 5, and they also cast the same part in Zamac 2 and had similar results. The unusual thing is that this part is cold chamber die cast. So they are casting zinc in a cold chamber machine. Although this isn't common practice, it is still done. So instead of using a hot chamber process, which would help us reduce gas or not entrain gas in the shot system, they're using a cold chamber process. And subsequently, then the parts are then polished, and then they're copper, nickel, chrome plated. Their scrap rates are ranging anywhere from 50% all the way up to 80%, and it's bubbles. And these bubbles are, if you remove the plating, it actually, in some instances, the zinc is actually flat. In other cases, the zinc is actually bubbled up. So basically, we've got 2 things. We've got outgassing, and we've got blisters forming in the coating. So as we discussed it, we started to look at the process, and that's the point they're at right now, is have determined, obviously this is outgassing and blistering that's occurring during the plating process. As a simple test, I had them just take some castings, put them in a furnace, raw castings, not not processed any further than as cast, and so that they could see a way to determine the trap gas right at the die cast process. So we just put them in a furnace, 400 degrees, for about 30 to 45 minutes, pulled them out, and they had blisters all over. So that was a way that they know they can work on the process, and then they can check the castings and see improvements in total gas reduction. We then went into what else can we do to reduce gas? Where's the gas coming from? And that's the stage they're at right now in determining all of the sources of gas and then eliminating every one of those sources. Now, we talked about that in one of the previous episodes of Ask Paul. So if you have other questions on porosity and reduction of porosity, you can refer back to that. And then I also included some training materials in those other in that other Ask Paul, so that if you need to, you can get those porosity reduction ideas. One other point I want to make is that they are casting this cold chamber zinc, and Zamac 5 has a very narrow solidification range. So it's similar to casting magnesium. So you've got to have rapid fills, and you've got to have a great response, not only of your fast shot system, but your intensification process, so that you're bringing the intensifier in and you're collapsing the gas or moving the gas out of the casting to the venting area prior to solidification. So zinc is going to solidify much faster than aluminum alloys. With aluminum, they have a larger solidification range, so that's also a variable that this caster needs to look at. They need to look at where's the gas coming from, but their process parameters, make sure they have a good machine to be able to cast this product in. Moving on to the next question. So this is kind of a broad question. And the question is, what are additive manufacturing processes, and what are the machines that are being used for additive manufacturing for die casting applications? So I want to give a little bit of background, then we're going to get into the answer of this particular question. So currently, NADCA has 3 active additive manufacturing projects. We've got a couple other projects that are pending review and pending approval, but the ones that are active are currently a literature review and benchmarking for additive manufacturing. And that's going to be more of a publication of additive and how it applies to die casting. This next project is evaluating material and powder size characteristics for 3D printed inserts. This is being done by the lead PI is Yoli Chu, Dr. Yoli Chu from Ryobi, and Jiamin Wang from Purdue. And there we're looking at not only the type of powders, but also the powder sizes. And we have determined that, if you've got any kind of large powder, 45 micron or larger, you're actually going to have defects that are going to form in the printed materials. So you want to maintain a smaller particle size when you're using powders for printing inserts. The last one is a conformal cooling project led by Worcester Polytechnic, WPI, and that's Dr. Carl Soderhelm, and that's the rapid creation of tooling with conformal cooling. And that's looking at a lot of different conformal cooling projects. And the ultimate goal for NADCA is not only to show the benefits of conformal cooling, but then to develop standards for conformal cooling. So when we're looking at additive manufacturing, we're basically doing this for a few reasons. We want to address the thermal problems in our die cast tooling and that are related to quality issues. So if we're seeing shrink porosity, we're seeing leakers, those kind of events, those are things that conformal cooling can assist, because we can then move the cooling right down to the shrink areas where shrink is forming. We can change the solidification in those areas. So we can change that thermal balance, and we can solidify rapidly in those shrinking areas. Okay. We can also increase productivity by increasing the cooling capacity So we can actually see cycle time reduction. So if we have a biscuit that's blowing up and we just want to use conformal cooling on the shop block, we can actually increase the thermal transfer by moving those cooling lines closer to the surface and in a more uniform pattern to remove heat. So the biscuit is now not setting our process. And companies that have done that have seen about a 10% reduction in cycle time by putting in shop blocks that have conformally cooled components. Another item in using additive manufacturing is just to reduce costs by reducing die maintenance and increasing tool life. So the idea is that if we're having heat checking, we can use conformal cooling to get a better thermal balance of our die-cast tooling. So we have an insert that's seeing a lot of heat checking. We can change the conformal cooling so that the insert is more uniformly heated and cooled, and we're not seeing large temperature gradients. Those large temperature gradients are going to lead to heat checking in our tooling. So we can actually increase tool die life. Now, to get into the answer, we're going to talk about the different additive manufacturing processes. So here's a start of a list, and these are all the different processes that are used. So we have select laser sintering, electron beam melting, laser powder bed fusion, direct metal laser sintering, laser metal fusion, laser powder bed, and then we've got intelligent fusion technology. That's a trademark name by a specific company, very similar to powder bed fusion. And I want to say the same thing of this DMLS, the direct metal laser sintering and laser metal fusion. All of these processes are very similar to powder bed fusion, or the other way to say it is powder bed fusion is very similar to these type of processes. So they're all using a powder, they're using lasers to solidify that powder and then put new layers on and then build the 3D components up. I've included a website here, and I'll repeat this website in another slide. But if anybody wants to go out to this website, it's going to show you all of these processes and all the powder bed fusion equipment that's being used. Now, I did not include any direct energy deposition, which is a different type of additive manufacturing. And directed DED is usually used in repair, and some die casters are using that in repair of their inserts. So it can be used for repair or it can be used for new components. Other additive manufacturing processes are magnetojet, which is MJ, and this was pioneered by Vader Systems. This is actually using a liquid metal and building it up from that. And then we've got MIM, metal injection molding, and then direct light processing, and then nanoparticle jetting, and that's using ceramic and metal together and combining those materials and then building up a 3D component with metal and ceramics. And then we have 3D printed and sintered parts. Now this is commonly known as binder jetting. There's several different binder jet machines out there. And basically, binder jetting is using a binder material with metal. So they're using plastic that has metal contained in it. And they're actually using that like in a stick form. And they're doing the welding process, but we've got the plastic embedded in there. So once the parts are printed, you have to use a sintering process to remove the plastic. So, and then when you sinter the parts actually lose volume and they then get a final shape. So you actually have to 3D print the parts slightly larger and then use a sintering process. So when we're doing that 3D binder jetting, we're printing it and we're printing it with metal that's bound in a plastic carrier. And then we're washing it. So once it's printed, we're actually using some sort of debinding fluid to remove or dissolve the plastic, and then we're sintering it. So once we sinter it in a furnace, we're actually solidifying that part, and we actually lose a little bit of volume. When the parts solidify, from a powder state into a solid state. So this is 3D binder jetting. Direct metal laser sintering is using a laser, and basically it's laser is drawing on the surface of the atomized powder. And so once again, it's very similar to powder bed fusion, but it's drawing on the surface, and then they squeegee a new layer of powder over the top, and then the build plate drops down, and then they bring the lasers in and they do it again. And they laze the material one more time. So when you're using DMLS, we're using pure metal powders to produce parts with properties that are typically better than those of raw materials. And because we have that rapid melting and solidification, there's a lot of work going on in this and in powder bed fusion to actually characterize the mechanical properties. Because when we're using powder bed fusion machines, we're actually determining that if you're building in an X axis or a Z axis, you have specific properties. But if you're building in an XZ axis, so on an angle, you actually have different mechanical properties. So there's a lot of work going on in all of these processes to look at the mechanical properties of each one of the processes. So I've just got some charts on DMLS, once again, very similar to powder bed fusion, just to show some of the properties, tensile yield, elongation, and hardness. So this is an aluminum alloy. So just like our aluminum die castings, this is an aluminum alloy with a tensile strength of 37 KSI, a yield of 20 KSI with 10% elongation, and a hardness of 47 Rockwell B. Not unlike our die casting. So this is actually a 3D printed aluminum alloy. And then we've got cobalt, chrome, cobalt, Inconel, titanium, stainless. So we have several different types of materials with tensile yield and elongation. And when we look at the DMLS or the printing of aluminum or these other alloys, and we compare it to the wrought or the die casting, we can see very similar properties, 37 KSI to 43 KSI for tensile. And then for elongation, once again, wrought die castings are anywhere between 1 and 4 and 5%, unless we're doing structural castings and using either the oral alloys or manganese with low iron alloys, which can get up to the 8 to 15% elongation. But once again, printed and die cast similar alloys like a 380 are going to have similar elongation properties. So moving from the properties to the actual equipment, so this is a list of printers that are available today. And then at the end of each one of these printer names, I put down the type of printer that it is. So we've got an SLM 280, that's a powder bed fusion machine. 3D Systems has a printer out, and those are powder bed fusion. Mark Forged is a company that is providing 3D printing, not only in metals, but in plastics and other thermoset materials. And their system for the metal is called the Metalex system, and that's a binder jet system. So that's a system that you're going to then have to wash and sinter the materials after they're printed. Then we've got AddUp, and those are laser beam melting, electron beam melting from Arcam. Concept Laser has one that does laser sintering. And then Concept Laser and GE have formed together, and they've got a direct metal laser melting system. Once again, very similar to powder bed fusion. And Chrysler Kokomo just purchased this type of 3D printer that they put into their Kokomo facility. We got DMG Mori, and they've got a direct metal laser sintering system. EOS, they're a large player in this product, in this field, and they've got a couple processes. So they've got selective laser sintering and then direct metal laser sintering. Renishaw has a powder bed fusion. Sysma has a laser metal fusion. SLM, once again, has a direct metal laser sintering. Trump as a direct metal fusion. Once again, very similar to direct metal laser sintering, similar to powder bed fusion. Aconity 3D has a laser powder bed. Matsuura has a powder bed fusion and subtractive manufacturing in the same machine. So they actually have it so they're printing, and then they actually have machining operations inside there that they have subtractive processes, so they can come out with a more near net shape or a finished product. Velo 3D has a powder bed fusion process. Now they have trademarked their particular process and are now calling it intelligent fusion technology. And then the last one I've got on here is Aurora Labs, and they've got a powder bed fusion and direct energy deposition in the same machine. And once again, this is the website. You want to go out and look at these printers. They give descriptions. We talk about all the different attributes of each one of these printers and the manufacturers of those 3D systems. So just to kind of recap here in the next couple of slides, when we're printing, we're going to be printing for cores, details in our die-cast tooling. We can use laser cladding or direct energy deposition to do some repair of die-cast dies, shot sleeves, that kind of stuff. Laser repurposing, so we're using direct energy deposition to repair our tooling. We can also 3D print castings or aluminum parts, and then some manufacturers are using that to manufacture short-run products. So in the same machines, you can use different alloys. So we can be using stainless steel, H13, tool steel, A2 or D2, titanium, Inconel, copper. We can once again use the same machine to use it for aluminum, nickel, titanium, cobalt, or marging steels. So right now, the project that NADCA is doing, we have done H13 and we have done marging steels for steel inserts. Now new powders are being developed as we speak. So there are several different companies out there that are making powders and they're working on powder size and consistency, which is going to lead to better prints and better die cast applicable tooling into the future. So that's a quick overview of the processes and the different printers that are out there to help service the die cast industry and the rest of the world and all the other industries. Moving on to our final question of the day is, what is the correct operating range for A383 holding furnaces? Currently, they run theirs at plus or minus 15 degrees Fahrenheit. We're being asked to hold this to plus or minus 9 degrees by one of our customers. Do you think there's a big difference in these ranges? If so, why? All right, so as we look at furnace control, we just want to consider a few things. So we're going to consider three things. Dimensional control. So the furnace, the temperature of the metal that we're alloying in, that we're ladling into our tooling, is going to physically control the dimensions of the final product. Okay, so alloy temperature can impact casting dimensions. Process control is another one. So if we have die temperature variation, that can lead to slide issues or closing issues. If we have different areas of the tool growing at different rates based on the metal temperature that we're putting in. We'll talk about that here in a minute. And then equipment variation. The thing we need to consider is that we're measuring our metal and we're using thermocouples to measure. And thermocouples, frankly, don't last forever. So we'll talk about thermocouples in just a minute. When we're talking about dimensional control, we're talking about when the casting temperature varies. So our metal temperature is ranging at a plus or minus 15 or a 30 degree total delta T. That can lead to changes in casting dimensions. Although that's going to be small, Now, a 30-degree swing in temperature can have up to about a 4/1000th of an inch change over a 10-inch distance. Now we can calculate that. This is just based on the law of thermal expansion. So this is the actual equation. So this equation says that the change in length of an object is going to be equal to its coefficient of thermal expansion times the original length times the change in temperature, or delta T. So if we have a 30-degree swing, that becomes our delta T. We have an original dimension, and then we have whatever the material is. So the coefficient of linear expansion of steel, the expansion of aluminum or zinc. So whatever the casting materials are, we can calculate the change in length. So if we're looking at die temperature changes, and we're looking at process control, and we're now ladling in something that is 30 degrees hotter. Now the change isn't going to be immediate, but wait 2 hours, wait an hour and a half. And if you're ladling in something that's 30 degrees hotter, the temperature of the steel is actually going to grow. And it's going to grow proportional to this equation. Okay, coefficient of thermal expansion of the steel, the original length of the steel, we're going to have a new length. So the die could be running hotter, and the tool is going to grow. We have a new casting dimension. And once again, depending on the size of that and the total variation, it can lead to dimensional changes. So if you've got a casting that's frankly plus or minus 10 thousandths or has a total tolerance of 10 thousandths of an inch, it's probably not a concern. But if you've got a casting that you're trying to hold, plus or minus a thousandths or plus or minus a thou and a half, that could be a concern. It could be a concern if your metal temperature is varying and you're trying to hold an as cast tolerance, because you're now affecting the steel, affecting the process, and you're dimensionally affecting the casting. So if your customer is asking you to hold something tighter, frankly, I would go back to the customer and say, why? What are we looking to do? If we have general tolerances of plus or minus 10 thousandths or anything critical we're machining, then frankly, holding a tighter temperature is just that, holding a tighter temperature. It's not going to affect the end product. So I think you should go back to your customer and ask, why are we doing this? The last thing I want to touch on is basically equipment variation. So the equipment I'm referring to are the thermocouples that we use to control and monitor our furnace temperatures. So, what is a thermocouple? Well, it's an electrical device consisting of two dissimilar electrical conductors. These electrical conductors, form electrical junctions at different temperatures. And then the thermocouple then produces a temperature-dependent voltage as a result of a thermoelectric effect. So this voltage difference can be interpreted as temperature measurements. So we as a die-cast organization and an industry are using these thermocouples for temperature sensors in all of our furnaces. So as a commercial component, these are inexpensive, they're interchangeable, they have a wide range of temperature measurements that we can do, and frankly, they're used in all of our processes, in our main furnaces, and our holding furnaces, and our laundry systems. So we're using these thermocouples. Thermocouple accuracy, it can't get down to under 1 degree Celsius or under like 1.5 degrees Fahrenheit. If you're trying to hold things that tight, you have to go to a different type of thermocouple. But they are good, consistent units to measure temperature. The issue with a thermocouple is the aging. So every thermocouple is going to have some lifetime to it, and that lifetime is dependent on what's called the Curie number, and the Curie number happens when the material, the dissimilar materials, those alloys that are in the thermocouple wires, okay, when they reach higher temperatures, they start to break down. So we start to see metallurgical changes in those due to prolonged exposure to those high temperatures. Once we start to see that, then our measured voltage is going to differ from the actual voltage. So we just need to be aware that if we're trying to hold plus or minus 3 degrees or plus or minus 10 degrees on our furnaces, we could see plus or minus 2 or 3 degrees just because of thermocouple wear. And that's the device we're using to measure. That's the device our controllers are using to hold our metal temperatures, and they're going to break down over time. It's just a matter of time because all thermocouples are going to age. So some general considerations or answer is that, you know, plus or minus 15 degrees, you know, that's pretty decent. Plus or minus 10 is better. It's typically doable, and it's doable if you refill your furnaces on a very consistent basis, and if the metal coming to your holding pot, either through the launder system or by bull ladle, is consistent in temperature. So if I'm bringing down hot loads, if I'm bringing down cold loads, and I'm trying to fill up half of the furnace, so 1,000 to 1,500 pounds, I'm going to affect metal temperature dramatically. So if we, as a general practice in die casting, try to fill our furnaces when they're about 10% of the total volume. So if we have a 3,000 pound holder, we want to fill it when we've emptied out about 300 pounds. Because regardless whether we bring a hot load or a cold load, at a 10% volume, it's not enough to dramatically change the overall temperature of the furnace. If we're bringing down a full 1,000 pound ladle or a 3,000 pound holder, then that's 30% of the volume. It's going to affect the overall temperature. The other thing is what I've already talked about, and that is depending on the sensitivity of the part. So if you have a part that has very tight tolerances, the furnace temperature is going to be something we're going to want to control, because as the furnace starts to range, it's going to dimensionally affect your casting. The other thing die casters like to do is pour as low as possible. So if we don't need to, we don't want to pour 1,250 degree metal. We want to pour 1,220 degree metal, because that's just 30 degrees more temperature we need to remove from the process. So wherever we develop our process at, that then sets our dimensions, and we want to be able to pour at those lower temperatures. Okay, so tighter tolerances are going to need tighter ranges. So that comes down to this dimensional control. And if we're holding very tight tolerances, then maybe plus or minus 10 or plus or minus 15 isn't going to be good enough. For the process control, I touched on this a little bit, but if our metal temperature is changing, then our die physical attributes are changing. So all of a sudden our slides, if our slide is being cooled and the retainer around it or the cavity around it is being heated up dramatically, that could create fitting conditions. And if the slide's not fitting correctly, if the cover and ejector are not coming together correctly, then we could start to see potential flashing due to temperature variation. And then obviously the equipment variation, we touched on that with the thermocouples. They will age, and you will lose some ability to measure temperature over time until you replace those. So that concludes our question and answer session for today. If this sparked any questions that you have, or if you have additional questions, please send them in. We're going to be doing another live question and answer session at another date. So if you guys have any questions about today's event, I'd be happy to answer those. We have materials on our website that people can reference, or if you have questions, you can email me. My email's here at the bottom, and I'd be happy to get you materials. From the past episodes, several people have asked for some of the equations or some of the spreadsheets, and I've gone ahead and sent them out to them. So if you have additional items that you would like from this, please let me know, and I will get that for you.
Thanks, Paul. So as Paul said, we're going to open up for questions. There are a few ways that you can ask questions within your control panel. There is a text box. If you click within the text box, type your question in, hit send, and we'll get that in on our end. The next thing that you can do is if you're calling in on a phone or if you have a mic set up, you can click that little hand icon. We'll go ahead and unmute you and you can ask your question out loud. Again, please feel free to email us. Paul's email address is up on the screen. So maybe you don't have a question right now, but you think of one in a couple of days or you need clarification on something, please feel free to reach out to us either directly to Paul or to anyone at NADCA, honestly, and we will get those questions over to Paul as well. As Paul mentioned, we are always willing to help. We also host these recordings on our website. So if there is something you did want to share with somebody, please feel free to do that. That will be up on our website by the end of the day today. So a copy of the PDF as well as the recording is available there for you guys to review again. So with that, we're going to hang out on the line and see if any questions come through. All right, I don't see any questions currently in. If you're in the process of typing in a question, if you could click that little hand icon, that'll let us know that you're typing, and we should hang out on the line until that question comes through. All right, I don't see any hands raised and I don't see any questions coming through. I see a number of people dropping off the line. So with that, I want to thank everybody that attended today. And Paul, thank you for presenting. And we look forward to seeing you all on the next edition of Just Ask Paul. Thanks, guys. Have a great rest of your day. Bye.